So in this video, I'm going to discuss the coin change problem. See, the problem says that given a set of coins C, C1 to Cn, and value V, find the minimum number of coins needed to change V into lower denominations using set C. The assumption is that the C has infinite number of instances of Ci. Let's take an example. Suppose C has 3 elements 1, 5, 8, and to obtain the value V, which is 10, 10 can be written as 8 plus 1 plus 1. So it's a greedy approach, right? We take the higher denomination first and lower denomination at the last priority. So it gives you a greedy approach, and number of coins used here are 8 plus 1 plus 1, which is 3 coins. But if you write this 10 as 5 plus 5, and it gives you an intuition that we can also use even 2 coins, right? And by this strategy we go for a dynamic approach. So now number of minimum coins required are 2. In order to solve this problem, let's consider set C, which has many coins, okay, different values of coins, and suppose we are at the ith coin, and the solution for the I minus 1 up to 1, we know the solution for that, okay? By miraculously we know the solution, okay? This is actually a kind of a strong induction, we can say. But anyway, we will define a function which will take 2 inputs and arguments, because see, in this problem we have 2 parameters. One is the number of coins we are including. In an array we have many coins, different denomination coins, and we are including the how many different kinds of coins we can include it, and the value V that we want to achieve. So we define mi comma V as the minimum number of coins to construct V using C from 1 to up till I. It is not I plus 1, it is only I till the I, okay? So a recursive case includes 2 things. Firstly, shall I include the ith item or not? Okay, if I include the item, it means I'm increasing the number of counts the coin would be included in the back, right? So if I include it, okay, I should add 1 coin, okay, which is add 1, then take the minimum coins from the previous solution, right, from the previous one. So we have to take the solution from Ci to I minus 1. Okay, I will tell a different case where we can use it, but for now just focus on this, that we can have the solution from the previous solved solutions, okay, previous solved problems, subproblems. So mi minus 1, and indeed we have already used up that Ci cost. Then obviously we can include the remaining value from the previous coins, which are before the I, right? But if this j minus Ci, which is this quantity, right, this quantity, let me show you this quantity here, this includes that if it is negative, then we have to exclude that item. You can take that item because it is already taking much space and value will be not achieved, right? So we have to take the exclusion. But suppose you don't include that ith item, right? You don't add any coin, which is add 0, and take the minimum coins from the previous solution, previous subproblem. So C1 to up to Ci minus 1. So the solution goes like this: mi minus 1 and j minus 0. Why 0? Because we have not added any coin, right? And we haven't add coins, we didn't have any value to it, right? But do you think it is a correct solution? No. See, we have infinite many instances of the coins, so we can use as many times as possible. So in this previous case, in the inclusions case, we can erase this 1, okay? We can erase this 1 because we can reuse that same coin and we can add up to the amount V, right? So solution for that ith item can be given by this solution. Now let's check the base case. Now checking the base case, we have two conditions. The condition number one is if, let's say, there are no coins available. See, this is the number of coins which are 0. If there are no coins and you want to achieve a value which is positive, you can't have any number of coins because you don't have any coins. That's why it will take infinite many coins to achieve that value v. Okay, but let's say you have some coins. Okay, you have some coins, but the value you want to achieve is 0. So obviously you don't need to include any number of coins for any ith item. Okay, you can have 0 many coins. So once you've understood this code, let's go to the solution where I have done the coding. Okay, so this is the code I have written. Okay, so M is a table which has 4 rows and let's say it is 70 columns. I'll just initialize it because it's a global, so all the values will be initially 0. So I made a function which is min value. It returns the minimum value between these x and y. Right, so the solution goes like this. You have initialized a set which is C, and it is having 158 as the coin denominations. The number of coins are three types of coins, and we want to add up these coins to value 10. Okay, so as I mentioned that it will have two parameters, so obviously it will have a dynamic table of rows and columns. Number of rows are 3 and number of columns will be 10. It is not actually 3 and 10, it will be one more row and one more column. So anyway, for each row and each column we have many cases to be encountered. So consider this case, base case. If the number of coins are 0 and if you want to construct a value which is greater positive, it will be infinity. So I have mentioned that this 999 is equivalent to infinity, right? It is infinity. And if the value I want to achieve is 0, so obviously you need no coins at all. But if I say that this j is less than ci minus 1, okay, so I will make it clear why it is ci minus 1. So I've already mentioned that this c, you can take this sign here. Okay, I've already mentioned this condition. If it is negative, means we have already found a coin which is having higher value than we want to achieve. Then it is a negative value, right? The difference should be negative and we don't want it. So obviously we have to exclude it. So we go for the previous solutions from the previous row, okay, to achieve the same amount, j. Okay, the last condition is we have to add 1. Okay, same condition, the same condition here, and we can either exclude it or include this item. And if we include it, we have to add 1. If you don't include it, we have to add 0. Okay, so that's it. And why? You have noticed that we have used ci minus I here and also here. This is because the index starts from 0. That's why we have just maintained a simple tweak that if there's an I, you can just decrease the index by 1 so that we can reach 0. That's it. That's it, very simple. And I should not say simple because it takes a lot of time to analyze it. So anyway, I'm running this code. It should give no error, and obviously it will give you some answers for 4 rows. Why 4 rows? Because there are 3 types of coins used and 1 row for the 0th index. Okay, and each row suggests you some important facts that we should be noted. Let me explain this. So consider a case where the number of columns represents the amount to be achieved and the rows tells you which coin I can use till now, okay, till the ith row, right? So let's consider this 4. Why it is 4? Because you can see that this is a third row, and it is up till second index, and this column indicates fourth, right? Fourth weight to be achieved, right? If I want to achieve 4 using this set, how many coins I need? Obviously 4, right? Because 1 plus 1 plus 1 plus 1 gives you 4. But if you see the next column, it shows you that if I have only 1 as a denomination and I want to achieve 5, then I have to add 1 5 times. That's why 5 coins are required. But if you see the next row, it gives you a better understanding that till the second row, means it is not second row, it is third row, I have 1 and 5 as my set, but I want to achieve 5, so the minimum coins I require is only 5, so it is only 1 coin. So till the last position and last column in last row, see, it is 2. Why 2? Because we have included 3 items, 1, 5 and 8. How can you make 10? In a very simple way. 5 plus 5, that gives you 2 coins. It completes the solution of this problem.